have looked at condition number 2, where both ends are pinned, and then what does it actually means? Okay, we know that L over R has been increased to 88.86. Then let's look at condition number 3. Okay, so condition number 3, which I'm going to get the image, which is this one. Okay, so condition number 3, as you can see, is one fixed end. And one pinned end. And as you can see, at point B, we know that force in the x direction, force in the y direction, and moment in the z axis is not equal to 0. Okay, so this end is what we call fixed. And for a pin for this case, right? For a pin for this case, what we can say that force x is not equal to 0, whereas force in the y and moment in the z is equal to 0. That's why you have this curvature over here, whereas down here is straight, as you can see down here. So what you observe down here, when this is the case, LE is equal to 0.7 L. So how does that affect our equation now? Okay, so we know that stress critical is equal to pi squared E over L over R squared. So this will be replaced by pi squared E over 0.7 L over R squared. So we have 0.7 L over R. This will be equal to square root of our pi squared, 200 times 10 to the power 9, and then the whole thing divided by 250. Okay, 250 times 10 to the power 6. Okay, so this will be equal to 200 power 9 times by pi squared divided by 250 power 6, square root 88.86. So the L over R over here is 88.86 divided by 0.7. So our L over R is equal to, now it increased to 126.94. Okay, so it's more resistance to what? To buckling, basically. Okay, and then our last condition, condition number 4. Okay, so over here. Okay, so for this case, both ends are fixed. Now this is a very interesting problem. When they say fixed, more or less is they are referring more about the moment. Okay, so we know down here when it's fixed, moment is not equal to 0. Same thing, moment is not equal to 0. Over here, we can say fx and fy are not equal to 0. But over the other end, fx is fx is not equal to 0, but fy is equal to 0, because there's a you to apply a load, you must allow it to move. Okay, so when they more or less, if they say it's fixed, it more refer to the moment is equal to what? Equal to 0. When it's pinned, okay, or when it's free, moment is not equal to 0. So for this case, the interesting thing now comes to this, okay? So what we have now is LE is equal to what? Now we can see LE is equal to 0.5 L. I'm not going to do the whole calculation again. So we know that 0.5 L over R is equal to 88.86. Okay, so therefore your L over R is equal to 88.86 divided by 0.5. Okay, so 88.86 divided by 0.5 is equal to 177.72. So the resistance of buckling increases. Okay. So like what I mentioned before, it's not just the length, it's not just the material behavior which is related to Young's modulus, it's not just the cross-sectional area, right? It's also depend on how the both ends are fixed that will affect the critical load. Okay. Now I'm going to do a example now, and this example has a lot of layers. When I say a lot of layers, you have to be competent in a lot of subtopic in strength of material. Okay, so let's look at this example. So this will be at our example. I cannot remember how many examples we did today. I think it's example number 3. Okay, so we're going to do example number 3. Okay. Okay. So now the structure beam below. Okay. It uses a 100 by 100 meter square bar. So the square bar. Okay, so B and C, this is the square bar. Okay, not square bar, square bar, and is 100 by 100 millimeter square and 25 millimeters diameter to support a load P. Okay, so this is the cable. And the cable has a diameter of 25 millimeters. Okay. The square bar BC is made of steel with a yield strength of 300 megapascal. So we are given that this is our stress yield. And the stress yield over here is 300 times 10 to the power 6 Pascal. And we are also known that the Young's modulus is equal to 200 times 10 to the power 9 Pascal. Okay. While the cable is made of high strength steel with a yield strength of 1800 megapascal. So we know that the stress yield, wow, this is a very strong cable. 1800 times 10 to the power 6 Pascal or 1.8 gigapascal. And it has a Young's modulus E, which is equal to 190 times 10 to the power 9 Pascal. Okay, that's a Young's modulus. Determine whether the structure can support a load of P is equal to 250 times 10 to the power or 250 kilonewton. Okay, so that's our 250 kilonewtons. So they want us to consider a few things. They want us to consider in-plane buckling only. And for in-plane buckling only, we're going to use a safety factor of 2 bars. Okay, and it's going to base on Euler buckling load. Okay, so when they say it's Euler, you have to find how both ends are fixed. Okay, that's the important part. The safety factor for yielding of steel is 1.5. Okay, so all these information are given. So there are three ways that this thing can fail. Okay, there are three ways. Okay, so let's look at three modes of failure. Okay, so mode number one. By the way, this question is given by the Professional Engineers of Canada. Okay, so what it means is foreign trained engineers that got their degree from, for example, from Saudi Arabia, from China. If they are going to become an engineer, they have to sit for an exam and they have to answer questions like this. Okay. This course, when I designed the test question, is also based on how the professional engineers exam any other foreign student. Okay, so that's the level I'm looking for, or I'm looking at. Okay, right. So this question, there are three modes of failure. Mode number one, or failure mode number one. Failure, or I won't call it failure. Failure mode number one, cable is AC. Okay. Failure mode number two, is where the stress BC, right, or member BC is greater than the stress yield. Okay, that is mode number two. Failure mode number three, in fact, I do apologize, it's not stress yield, it's stress yield divided by 1.5. Okay, because of the factor of safety. Okay, factor of safety is 1.5. So failure mode number three is due to buckling. Okay, is where the factor of safety due to the or the failure of factor of safety, like what we calculate before, has to be greater than 2.0. Okay, so remember the factor of safety note, the factor of safety is equal to P critical divided by P. Remember? Okay, so we're going to analyze these three modes of failure. Okay, so what we're going to do now is we're going to carry out thrust analysis. Okay, but before we go on, we know AC, right, is going to be under what? Tension. BC will be under what? Compression. Okay, if this is not obvious, I'm going to show you. Okay, and showing you is basically based on physics, nothing to do based on what previous experience you have. Okay, I don't want this course to be based on experience. Okay, I want it to be based on fundamentals. Young's modulus and elastic modulus, the same thing. Yeah, they're the same thing, Lee. Okay, right. So the next thing we're going to do, okay, we are going to perform thrust analysis. So when we declare thrust analysis, we are only consider axial loading condition only. Okay. Right. So we are going to apply, I hope you all remember this, the method of joints. Okay. at C to find the